Hello everybody. In this video we'll be covering one of the sections in chapter 7 of our textbook entitled Chemical Reactions. In this video we're going to be discussing aqueous solutions. So many times the chemicals we are reacting together, we wind up dissolving them in water. Water is what we would call a very convenient solvent to use, meaning that it's going to dissolve a lot of the different chemicals that we want to work with. And we call these mixtures of chemicals dissolved in water aqueous solutions. The reason that we would want to do this is because dissolving the chemicals in water helps them to react together faster. The water separates the chemicals into individual molecules or ions sometimes, and the separate free-floating particles come in contact more frequently so that the reaction speeds up. Okay, so if we want to get good contact between our molecules, we dissolve them in a solvent like water, and then they start moving around in the bulk of that solvent. They come in contact with each other more often, and when those molecules come in contact and they're in proximity to each other, that's when a reaction happens. So we can predict whether a reaction will occur in aqueous solution, and the way that we do this is we think about the forces that drive that reaction. In a little while we'll talk about solubility, and we'll be able to better predict whether or not we're going to have the formation of a solid. The formation of water is another good indicator that a reaction will happen. That is, that water is one of the products of the reaction. The formation of a gas is another good indicator, or the transfer of electrons between two of the species. And the reason for this is because of energy. Basically, the formation of a solid or water is going to release a lot of energy that's going to make and lead to very stable arrangements, so those are going to tend to be favored. The formation of a gas and the transfer of electrons increases something that we that you'll learn about if you continue on in chemistry, called entropy, and that's also going to be favorable for a reaction. So, as I said, if one of these forces is present, we're going to see a reaction happen in the aqueous medium. So when ionic compounds dissolve in water, the anions, the negatively charged ions, and the cations, the positively charged ones, are separated from each other. This is called dissociation. The cations and the anions are dissociating from one another. But it's not true that all ionic compounds are going to do this, because some of them are not going to dissolve. They're not going to be soluble in water. And again, we're going to talk about that in another video where we're going to be able to predict which ones will and which ones won't. When compounds containing polyatomic ions dissociate, the polyatomic group stays together as one ion. So as we've mentioned before, our polyatomics tend to behave as if they were just a single atom. So we're not going to have the polyatomics break down. They're just going to float around in their ionic form and basically take the place usually of an anion, although we do have polyatomics that are cations too. We saw that with the ammonia. So it's always important for us to recognize how to write out a chemical reaction for these processes, and dissociation is no different. There's a chemical reaction that describes it. Here we have Ki. We add it into an aqueous solution, and it dissociates. Its product is a positive potassium cation in aqueous solution plus a iodine anion in aqueous solution. If we pictured that, that means that we had these two bound together, and then they went into being separated ions. If we had copper 2 sulfate dissociating in water, we could write out an equation for that. Again, our polyatomic stays together, and we're going to picture that as having copper and a sulfate, and then it associates out into a copper ion and a sulfate ion. So electrolytes. This is a word that you've probably heard before in the context of like Gatorade or other sports drinks or stuff like that. Something that you know you need, but you're not really sure what it does. And what electrolytes are substances whose water solution is a conductor of electricity. And all electrolytes have ions dissolved in water. So if you dissolve in water and then you form ions, which we've seen ionic compounds tend to do, then you are going to be some form of electrolyte. And a way of picturing this is like if we had a battery here, right, and it's going to power this light, okay? Well, what if I disconnected the battery? So if I had these two rods separated from each other, no current could flow through this, and it couldn't power the light. But if I dip it down into a pure water, we're going to have no current going still, because the pure water can't conduct electricity. But if I start to add electrolytes like sodium chloride, all of a sudden I have ions in here that are capable of conducting electricity, and I would complete this circuit between these two probes, and then the light would turn on. So there are classes of electrolytes. Strong electrolytes, all the electrolyte molecules or formula units are separated into ions. Okay, so an example of this would be like sodium chloride. If I put salt into water, all of the sodium chloride is going to turn into sodium ions and chloride ions. Non-electrolytes, none of the molecules are separated into ions. So this is a classification where now we have something that dissolves in water, but the mechanism by which it dissolves is not to form ions. So an example of this is sugar. You can put a lot of sugar into water. You can put like a ton, right? Like you can go all the way up to like simple syrup or something like that, where it's really, really thick, right? But the sugar not being ionic, right, because sugars are just made out of all nonmetals, isn't going to break up into ions, and it's not going to make the water any more conductive. And then you have weak electrolytes. This is where only a small percentage of the molecules are separated into ions. So an example of this would be like acetic acid, which is like vinegar, right? So vinegar is a solution of acetic acid in water. Now, some of it's going to remain together without dissociating, and some of it will dissociate out into the water. So there's a balance between the two, where some is in its dissociated form and some isn't, okay? Weak electrolytes, you're going to have to add more of them to get the same level of conductivity that you're going to need in a comparable amount of a strong electrolyte. So let's end our conversation of electrolytes by talking about what types of compounds tend to be electrolytes. We've seen salts, ionic compounds that are water soluble are electrolytes, and they tend all to be strong electrolytes. Another one that you may not have considered is that most acids are electrolytes, pretty much all of them. And that's because they form those H plus ions that we've been talking about before, and they're going to have some other anions that correspond with those. There's this notion that you may hear sometimes about a strong acid and a weak acid. And a lot of times people get confused about what these really mean. They think like a strong acid is one that's going to like dissolve things or, be bubbly or something like that. And a weak acid is like something that you don't really need to worry about or something. And that's really not what we're talking about here. A strong acid is one that is a strong electrolyte. It's going to completely dissociate in solution. And a weak acid is one that is a weak electrolyte. It is entirely possible for there to be a weak acid that is very dangerous. Like a good example of that would be like hydrofluoric acid. It's a very weak acid, but it is capable of dissolving even glass. And it is possible to have a strong acid that is really not super dangerous to you, even though any high concentration of acid is going to be dangerous. It's not the strength of it that's going to dictate that. Another one that we haven't talked as much about is bases. So these form these hydroxide ions, HO minus ions, and a cation in water solutions. And they have the exact same sort of language used around them. There are strong bases that are strong electrolytes and weak bases that are weak electrolytes.